This is our lecture number 4 of magnetic effect of current. In this lecture, by the application of Biot law, we are going to obtain the magnetic field due to a circular current flow. First of all, we shall obtain the magnetic field at the center of a circular current carrying loop. Here, a circular current carrying loop is shown. The current is entering the loop and it is flowing in a direction clockwise and coming out of that loop. The radius of the loop is R, and this is the center O. And due to this current element dl, we are going to obtain the magnetic field at this center O. As the dl, the small current element, and R being the radius, and from here we can easily conclude that dl and R, they are perpendicular to each other. So if we use the standard Biot law, which is dB is mu0 by 4 pi I dl sine theta by r square. Here the theta, the angle between dl and r, is 90 degree. So we have dB is mu0 by 4 pi I dl, sine 90 is 1, so I dl by r square. So next, to obtain the total magnetic field at point O due to this current element, due to this total circular current carrying loop, we have to integrate. So B is integration over dB, and putting the value of dB, it is mu0 by 4 pi I dl by r square. Being constant, mu0, the permeability of free space I, and 4 pi r square, which are taken outside the integration, and we are integrating over the dl. And if we integrate over this whole circular loop, it will give us dl is equal to 2 pi r, circumference of this circular current carrying loop. So dl is 2 pi r. So just if we have mu0 I by 4 pi r square integration over dl, just putting the value of dl, it is 2 pi r. We have b mu0 I by 2r. And we can see the magnetic field B, the value of magnetic field B at the center is mu0 I by 2r, and the direction can be easily obtained by using the right hand thumb rule. And if we use the right hand thumb rule and put our thumb along the direction of the flow of the current, then the rest of the finger will curl along the direction of the magnetic field. So the cross mark indicates that the magnetic field at the point O will be directed into the plane of the paper. So this is the magnitude and the direction of the magnetic field due to a circular current carrying loop at the center of the loop. Next, let us consider again a circular current carrying loop and obtain the magnetic field at an axial point of the circular loop. Look here in this figure, a circular loop is shown in this figure, and the arrowhead shows the direction of the current flow. And from here, the plane of the loop is perpendicular to the plane of the page or the plane of the screen. That is, the loop is coming out of this plane of the screen. And the radius of the loop is A, the radius is A, and the current I is flowing through it in this fashion. So P is this is the axis of the loop, and P is the axial point where we have to obtain the magnetic field due to this current carrying loop. So now let us see. Here O is the center of the loop, the point P as a distance R. The axial distance is R from the point O. Now, as we know, this is the circular current carrying loop. Let us choose a current element dl, small current element dl, near about the point A at the top of the loop. As we mentioned, the plane of the loop is coming out of the paper, that is the perpendicular to the plane of the paper or the plane of the screen. So here dl is perpendicular to the S, as S is in the plane of the screen. So dl and S are perpendicular to each other. So theta is 90 degree between dl and S. And if we use the standard formula of Savarts law, here due to this current element, the magnetic field at the point P will be mu 0 by 4 pi ideal sine theta by s square, where s is the distance AP, the field vector here. So dB will be here, theta is 90 degrees, so sine 90 is 1, dB is mu 0 by 4 pi ideal by s square. So here we have seen that dB, the plane of the loop, is perpendicular to the plane of the page. So the plane of the loop is perpendicular to the plane of the page, and dB must lie in the plane of the paper. And it must also be from the Savarts law, you know that it must also be perpendicular to the S vector. So from here, due to this current element dl at the point P, dB points along the direction of PC. Look here, this point is P, this PC direction, the dB is pointing. So if we have this angle from the triangle APO, this angle is phi, then this angle plus this angle is 90 degree, and this PC being perpendicular to this AP, so this angle plus this angle also will be 90 degree. So from this to consideration, we can say that angle APO and angle CPO these two angles are phi. So these two angles are phi. So dB will have two components, dB cosine phi along the perpendicular to the axis and dB sine phi along the axis. So this is due to this current element near the point A. Now if we consider similarly a current element in diametrically opposite point that of A, that is the point B here, its magnetic field will also point along the direction of PD. And it will also have again two components, one along the perpendicular component along this direction, it is dB cosine phi, and another one is along this direction, which is dB sine phi. So from these two, dB cosine phi cancels out, and axial components adds up. So we have dB sine phi due to this one, and dB sine phi is due to the plane segment DL at the point B. So we have axial components adds up, acts along the direction from O to P. Along this direction, the axial components acts, that is dB sine phi. Now, if we consider whole loop, then we shall have a number of current elements there. So obtain B, we have to again integrate dB sine phi. So we have to integrate B dB sine phi. We have dB is equal to mu 0 by 4 pi I dl by s square, as we have seen from here. We have so, and sine phi, from this triangle we have sine phi is equal to A by S. So if we put all these value here, dB is mu 0 by 4 pi I dl by s square, and sine phi is A by S. So mu 0 I dl A S, these are all constant and taken outside the integration. So, and we have integration over dl. So if we integrate over dl, what we shall get? The circumference here 2 pi. So mu 0 I A by 4 pi s cube into 2 pi A, and therefore we have mu 0 I 2 for pi by here cancels out, 2 cancels out. We have mu 0 I s square divided by 2s cube, and from this triangle we have s square is s square plus r square. Putting all this value here, we have B mu 0. If we have n number of turns, here one turn is shown. If we have n number of turns in this loop, we shall have mu 0 NIS square by 2 into s square plus r square to the power 3 by 2. And the direction of the magnetic field will be along the positive x-axis, along this direction. So this is the value of the magnetic field, and it will be directed along OP. So this is the value of magnetic field into a circular current loop in an axial point. And for some special case, the value of magnetic field at the center. So if we consider at the center here, the R becomes 0. So if we have B is mu 0 Ni s square by 2 into a square plus r square to the power 3 by 2, at the center of the loop we put R equal to 0. If we put R equal to 0, we then have B is mu 0 Ni by 2 is similar to that of the result of the first case, what we have already discussed. And for special case 2, the value of magnetic field at an axial point which is very much far away from the coil, this R distance is very high. Then what will happen? R is very much greater than A, then A can be neglected compared to that of the R. So from here we can neglect A, we have R square, and we have from here R cube will be there, so B will be mu 0 NIA square by 2R. So these are the two limiting cases of the value of magnetic field, and there is the rule is shown for obtaining the direction of magnetic field due to a circular current loop. This is very much easy and known to all of you. When an observer look at the face of the coil, finds a current to be flowing in the anti-clockwise direction. Look here, in the anti-clockwise direction the current is flowing. Then the face of the coil will behave like a north pole. And if the current is flowing in the clockwise direction, the face of the coil will behave like a south pole. So this is the standard rule for obtaining the direction of magnetic field due to a circular current.